Thank you so much for coming after a long day of your work. Like you're here, like hopefully you're like really interested in these kinds of like astrobiology and Mars kind of stuff, like kinds of research that is going on, and that's why you're here, I believe. And I hope that I would not disappoint you by the end, in the end of 2 hours. I'll like briefly introduce myself. I'm Kaushik Mitra. I'm a postdoctoral research associate in the Department of Geosciences in Stony Brook University, where I'm working basically with experimental geochemistry. That means I do experiments which are more relevant for Mars-like conditions. So whenever we get a lot of data from Mars, sometimes we do not know what that data means. So I take a step back, I create Mars-like conditions in my lab setup and try and do experiments to understand more about why we find certain things that we see on Mars. What are the implications of having that particular mineral or that particular organic compound in the lab? So I do experiments to understand that. I did my PhD from Washington University in St. Louis in 2021. And after that, I joined Stony Brook University. I'm really interested in education and teaching, but I might not be as good as a teacher as you guys. You have been like, you're master teachers, you have been trained to teach to students. I have not, but I have got some experience. And through this, I'm like trying to gain as much knowledge from you guys as I expect you to get from me. So at the end of the course, please feel free to tell me what I did wrong and how can I improve upon my teaching skills. So this course is about the quest of life and habitability. Why do we care? Because like humans in general are really curious. We are curious about what things are happening in the universe. Space sciences is one of the frontiers of knowledge, like brain sciences is one of the frontiers, and I think space sciences is one of the other frontiers of knowledge. And we want to understand whether biology works the same way on different planets in the solar system and maybe different planets in our galaxy as does on Earth. Because we know mathematics works the same way on our planet as in any different planet. Chemistry probably works the same way, but we do not know whether biology works the same way as it does on planet Earth. So this is one of the biggest quests of humankind, like whether they have life, whether the biology of that planet is similar to what we have on Earth. So since I'm more interested in Mars because we have so much data coming from Mars, I thought like understanding why humankind, NASA in particular, have been following Mars missions, like there have been so many Mars missions, to understand this one big thing, like why do we have life, or do we have life anywhere other than Earth, and specifically in the case of Mars. So in this course, which is a 3-lecture course, we'll be trying to answer these questions. In today's lecture, we'll be specifically focused on the bigger picture questions. What is life? What is habitability? What, how, and where? You see, there is no when, because that's a really big question. Like, when did life happen? We do not know a lot. But if we can tackle some of the smaller questions, like what is life? What is habitability? Where and how can we find places which are more habitable than the other places? So in today's lecture, we'll be doing that. Okay. The bigger, I do not know. Cancel this. Right. So basically what we are trying to do in this 3-course thing is understanding the different aspects of life and habitability on Mars. There are no specific books that you need to follow this. I've designed this course for a very basic audience, but I follow these 2 books, like an introduction to astrobiology is like a very basic book that we have. You can read this book. This is meant for a very like normal audience. You can take a look. And for like more advanced audience who are really into planetary astrobiology, there's this book called Planetary Astrobiology that you can buy, or you can refer to your library. There is another book called Planetary Geosciences, which is this book, which gives you a basic idea about planetary geoscience. This has been like really helpful for me when I teach undergraduate students, and it's a really good read. So there are also, I imagine that you are taking this course basically for two reasons, perhaps. First, you are really inquisitive about Mars, life, astrobiology, things like that. And the second is you would also want to use the resources to teach in your classes. So you might know a lot of resources. There are two in particular that I want to like reiterate if you do not already know: astrobiology.com and astrobiology at NASA. So these are the two very big, very good resources that are available for all of us who can to go read about the different new findings related to astrobiology, related to Mars research. Really good big picture ideas have been presented in really simpler language. I highly recommend these two resources. Also, I have come to know about this resource, the NASA Community College Network, NCCN, which is under the aegis of SETI, the Search for Extraterrestrial Intelligent Life, the SETI Institute. With NASA, they have set up this amazing resource in which they are connecting subject matter experts like me to community college professors. And I think this should be available to all teachers as well. So what you have to do, I think you just have to go there, register yourself, and then you can be connected with subject matter experts, and you can have them talk in your class and have different kinds of resources. So you can have different kinds of reading materials, videos, apps, and games, and simulations, all these kind of things. On the left-hand side, you see these different filters. So this is a good resource that you can use in teaching your classes. So I just thought that I would just mention this. Okay, so this the videos in it are being recorded, and I hope that these will be available. I also record videos online and put it on my YouTube channel, so you can also watch these videos there. Since this is the first time I'm teaching in a very special class like this, in which the audience itself is an expert, so I do not know how much I'll be able to cover. The things that I will not be able to cover, I will record those things and put it on this website. How fast I'll be able to do this, I do not know, but sometime in the spring semester, I'll be able to upload all these different materials as video lectures on this cheesy sounding channel called Chemical Mindset. So if I'm not being able to finish something, these things will be available there. I'm also developing a website that will have all the resources that I'm going to have it in here. So there will be research papers, peer-reviewed research papers that will go along with the things that we teach and that we learn here. And there will also be blog posts and resources like NASA, astrobiology.com, and things like that. So I'll be giving links to those resources in the website that I envision, which doesn't exist yet, but that's what I think will happen. So big picture idea of what is going to happen today is we are going to start off by the definition of life. What does it mean, like life as we know it? We need to set up some basic regulations and like, okay, this is what we think life means. We just go over some basic definitions. Then we move on to a more broader definition of habitability and what does that mean in a planetary scale. Then we move on to the habitability zones in the solar system. So we have really hot zones. We have like Goldilocks zones, like you have heard about this story of Goldilocks, too hot, just right, and too cold. So we have habitable zones in the solar system. So we'll be looking into that. And then we'll be, so the habitability and the habitable zones in the solar system are the biggest chunks of today's lecture. And then we'll have a sneak peek into which planetary bodies in the solar system have the most potential for life. So we'll look into Mars, We'll look into some ocean worlds, which we know that have huge oceans just beneath their icy exterior, Europa, Enceladus, Titan, things like that. And then we'll just have a brief discussion about why we think Mars is habitable, or why do we think Mars might be habitable in the past, in the present, what are the things that are going on. In the next lecture, we will move on to the historic to modern like missions that have been that have gone to Mars, and what have been their findings. Did they find life? Did they find evidence of water? Did they find any minerals that said there was water in the past? Are there geomorphological evidences, geochemical evidences of liquid water? Because essentially, at the end of today's lecture, we'll see finding life is equivalent, has become equivalent to follow the water. So if we are following water in the solar system, and the same thing goes for Mars. So do we have enough evidence that we can surely say that Mars has liquid water on the surface? If not liquid water, is there water in the atmosphere or in the polar caps as ice, stuff like that? In the third lecture, we'll move into the more specific data right from the rover. So we'll specifically focus on the Opportunity rover, the Curiosity rover at Gale crater, and the recently landed Perseverance rover at Jezero crater, and see some of the really exciting results that are coming back. We'll briefly discuss meteorites, because there have been, in the past decade, we have found extremely interesting results from one of the meteorites called Black Beauty, you might have heard. So we'll briefly discuss about that. And we'll end by what the next decade has for us in terms of Mars sample return. So as Perseverance rover is collecting these Mars sample returns in these small caches, and we are planning to get them back, what entails there. So there we are going to end the lecture. Now, astrobiology typically means like biology of the stars, but what we are trying to understand is not the biology of the stars. Astrobiology as a broader term doesn't mean the astrobiology of the stars, but anywhere in the solar system or in the galaxy. Anywhere in our galaxy, we would want to know, is there potential for life? So this is an image taken by the Hubble Space Telescope. So it was directed towards a seemingly uninteresting part of the night sky, black, and it captured the like different kinds of light, visible, near infrared, X-ray, all these kinds of different lights from the EMR, the electromagnetic spectrum. And after analyzing these, we got this spectacular image, and all these small dots that we see in here are galaxies. So this was extremely this was a big phenomenon in astrobiology, because understanding that there are so many different galaxies with billions and billions of stars in them, and each of these stars having so many planets in them, brings us a huge opportunity for us to find out and talk about astrobiology. So if there are billions and billions and billions of stars in the solar system, is it not possible that some of these galaxies will have some stars that will have a planetary system around it, just like our solar system, and it will have planets just right for life to grow? So Metrodotus, like this, I like this because it puts things into perspective. Life on Earth should not be special, given like it would be highly improbable that Earth is the only planet that has life. Whether we'll be able to communicate with them is the question. But personally, I do not have any doubt that there are other like life forms in the solar system. They can be intelligent, they cannot be intelligent. That's a different question. Whether we'll be able to communicate with them, that's another question. But I believe that given the probability, just the sheer amount of like the sheer number of galaxies and planets that exist, there should be life at least somewhere in our universe. So this is the famous Drake equation. We are not going to linger on the Drake equation. This was formulated by the founder of SETI. So he gave this equation in which he was trying to find out whether or not it is possible for us to have planetary bodies that have intelligent life in them. And that's a function of so many different kinds of things. So that is dependent on the rate of formation of stars, how fast things are forming in our universe, and how many of those solar systems. So this is like a molecular cloud that you can see in this image. So how many of those planetary systems have, how many of those galaxies have planetary systems in them, and how many of those have suitable conditions for life? So this is the thing that I tend to focus on, because this lies just in that region in which I'm interested, because we are trying to find out those conditions that place habitable conditions. Like this is the factor that is the most interesting to me, because this will give you the number of planets in a particular solar system that will have the right amount of conditions for that planet to be habitable. Then, of course, there will be a fraction in which life can actually appear, not just the chances. Being habitable is one thing, and life actually growing on it in one thing. And the fraction of intelligent life, fraction of civilization that have the technology to communicate with us, and the length of the time that the civilization actually exists. So mostly we'll be focusing on this N part of the Drake equation. Not going to linger on it a lot, but I mean, this is interesting idea. But the question for this audience is like, why care about Mars? Why do we care about Mars? We know that life exists on Earth, and so this is the geological time scale of Earth, in which the Earth formed somewhere around 4.56 billion years ago, and then we have the oldest microfossils somewhere in this region. So this, what does oldest microfossil mean? Oldest microfossil mean that we have clear evidence that life existed at 3.5 to 3.4, that range. So in that region, we have some microfossils that said that are evidences of past life. That means somewhere between 4.5 to 3.5 billion years, this is the region where there was origin of life on Earth. We do not know when. And an important question for this smart audience is why? Why do not we have so much evidence of past life if it existed? Why do we have evidences only ranging from 3.5 billion years and forward? Why do we have that? Why don't we have any rock record previous to 3.5 billion years? Yes?
You needed oceans and sedimentary rocks. I remember learning like our fossil understanding was much better when sedimentary rocks really was able to form.
Any other?
Did we have any solid rock at that point, or were we just kind of a pool of magma of, you know?
So it started off, so in the Hadean, we started off with like liquid, but it soon cooled off, and we soon had primary crust that formed. But we have tectonics on Earth. So the tectonics killed all these different rocks. It's recycled all these different rocks. So since we have tectonics, we do not have the oldest rock record in which life actually formed. So the oldest we can go is like 3.5, 3.3 billion years. So life may have formed before that, but we do not have any specific, we do not have much of those really, really old rocks. We do not have those rocks so that we can date them or analyze them. Mars is a whole different story. Mars, the surface of Mars is really, really old. So 50% of the surface of Mars is like really old. So you see this first 1 billion year of history from 4.5 billion years to 3.5 billion years, Mars has those rocks. And 50% of the surface of Mars are those really old 1 billion, like really the first billion years of rocks are preserved on Mars. But so what? It was preserved on Mars, not on Earth. There are similarities between Earth and Mars, and that's the important point. There are so many. Mars and Earth both are terrestrial planets. That's one similarity. The second is the axial tilt of Earth and Mars are very close to each other, at least currently. So currently, the Earth and Mars both have an axial tilt of about 23 to 24 degrees of axial tilt. That means Mars had seasons. Also, the rotational period of Mars is also very similar to Earth. So the Earth rotates every 24 hours. It spins. So the rotation period of Earth is about 24 hours. Of Mars, it's about 24 hours and 30 minutes. So really similar. So there are staggering similarities between Earth and Mars. And if we can understand, if we want to understand how life originated on Earth, we would want to know how, because we do not have that rock record on Earth, the second best place to go is Mars, because we do have those rock records. Now, the question remains, like, how did life begin? Previously, there was a theory of spontaneous generation. Like, imagine yourself as like 5,000 years ago, and you see rotten meat lying, and then you see like larvae or like microbes growing on that rotten meat. So what would you have thought? You have something which is rotting, or you have some inanimate thing which is not life, but from that, life can spontaneously begin. So that was the general idea. Louis Pasteur, as the scientist shown in here, he showed that if you sterilize, if you sterilize surfaces or sterilize biological instruments that are being used in the lab, you can prevent the growth of bacteria. That means he kind of put this idea of spontaneous generation to rest. That means he said, if you sterilize things, life will not grow. That means you need life to form life. So you cannot form life from inanimate things. But that meant like all life forms will form only from existing life. But the big question now remains is, what about the first time life originated? That's the big question that we are still trying to answer. So there is a Simon's collaboration of the origin of life. And I am part of that research objective. And we are trying to find out, how did inorganic life form organic life? Like, how did that first bit of organisms form? So you can also go to the Simon's Foundation for the Collaboration of Life, SCOL, and they have listed down critical questions concerning the origins of life. And you can engage your students and yourself into these kinds of questions. So it's a very good way of like thinking about how life started. It gives you some starting points. And you can also read about some of the research that is actually going on this idea of the origins of life. How did life form from inorganic to organic for the first time? Really interesting questions. Now, let's move into life as we know it. Like, let's understand the definition of life, the really big picture. Also, I am not a biologist, so I will quickly move through this. If we just understand a working definition of life, life is anything which is a chemical system which is self-sustaining, that can replicate, that can produce offsprings, and that offspring should be able to undergo Darwinian evolution, survival of the fittest, and this whole story. I'm not going into it because it merits its own class. So just understanding that, okay, it's a self-sustaining system which is capable of Darwinian evolution is how we astrobiologists take the definition of life and we run with it. Now, when you have Darwinian evolution, we are seeing animals and things like that on right now. But when we understand that life originated from something, so it went through genetic evolution. So what we are standing right now might not have been similar but it might have gone through genetic evolution. So we can track these things back. So that's the idea. Now, generally, there are 3 types of organisms in this world: bacteria, archaea, and eukarya. So bacteria is the simplest, it's the single-celled organisms. Archaea is also similar to bacteria, really single-cell organisms, but they have little distinct cell membranes, and they display a broad range of metabolisms. That means archaea can eat a lot of different kinds of food, and it can survive in really extreme situations. And we'll bring in the idea of extremophiles in a little while. But bacteria and archaea are the single cell, and eukarya, like the multicellular organisms like us, we are a part of the eukarya. So generally speaking, these are the 3. Now, when you take these 3 different kinds of organisms and you trace them back, you reach to something called the LUCA, the last universal common ancestor. So that is the thing that will give us the idea that what was that one big grandparent that originated every different kinds of organisms in our solar system. So a lot of the astrobiological explorations are to determine this LUCA, the last universal common ancestor. So this is called the tree of life, and this is really complicated. So that the diagram was really a simplistic form. So it is actually a really complicated diagram, as you see on the left. On the right is another really simplistic form, which tells us that, okay, Earth formed at some point, and we'll talk about the prebiotic soup. Life then formed its first organisms, and that first organism went through Darwinian evolution and came to this LUCA, and then you form different kinds of organisms. So this whole tree is based on RNA genetic code. So there are DNA and RNA. So the biologists have come up with this idea of like understanding the RNA of all these different kinds of organisms and setting them up on a tree, which will, like, the closer you are on the tree, the more genetic relationship you have. The farther apart you have, the farther away you go. But when you move and get to the LUCA, that's what we are trying to find out. Now, the LUCA is this is a grandest form of this show that I found out, that there's a show that tries to find out your ancestry. So finding the LUCA is the grandest form of this TV series. Now, understanding the LUCA is important because that will give us an idea about what kind of environment was there that facilitated the formation of this last common ancestor. So that's what we are ultimately looking towards, to finding out those environments that actually facilitated the growth of all these different kinds of multicellular bacteria, archaea, eukarya types of organisms. So a lot about this is what doesn't fall under my expertise. So I'm just like go ahead with this to this cute but scary looking image of the tardigrades, which is an extremophile. So when you look at the phylogenetic, like the tree of life, we see that a lot of extremophiles. So you see, this is the archaea branch, and this is the bacteria branch, and so this is the LUCA in this part. So we see that close to the LUCA remains a lot of these extremophiles. And what do you mean by extremophiles? Those kinds of organisms that can sustain at really extreme conditions of temperature, pressure, salinity, pH, radiation, and stuff like that. So we think that this LUCA was some kind of an extremophile, some kind of an organism that was able to sustain in an environment which was really hostile. What are the different kinds of extremophiles that we have? And please remember, why are we thinking about these extremophiles? Because LUCA is supposed to be some kind of like an extremophile. Now, the extremophiles can be thermophiles and hyperthermophiles, those organisms that can remain at higher temperatures like even at 50 degrees or 100 degrees, there are archaea and bacteria that can sustain and thrive at really high temperatures like this, like the hot springs. There can also be different kinds of extremophiles called the halophiles. These are those organisms that can sustain in high degree of salinity, like really concentrated brines, where most of the common organisms will die because of the higher salinity. These thrive, so there are halophiles. Really acidic conditions, acidophiles. Really alkaline conditions, alkaliphiles. The idea is, no matter what the different kinds of circumstances, there are extremophiles that can adapt itself to thrive and to, not only to like survive, but to thrive. So a lot of extremophiles are basically, we are trying to understand these things because they're really interesting. In this case, in which you see on the right-hand side, this organism, the D. radiodurans, was able to survive in really high radiation environments. It was able to survive in the high radiation environments. And why is it important? Because on Mars, we expect really high radiation environments. So if we think life might exist on Mars, it could be something like that. On the left-hand side, you see, we call it like endolithic bacteria, in which, so you see these green color, these are growing a few centimeters below the surface, so endolithic, below the lithic surface. And these are also extremophiles who have tried to grow in circumstances that was not favorable. So the surface was not favorable, so it went below the rock and started growing there. So life is really robust. That's the idea. So life can occur in really robust circumstances, really cold, really hot, low pH, high pH, and whatnot. But what we are trying to understand is the environment in which LEUCA thrived. So what kind of environment was there when LEUCA was actually forming? So to understand the environment, we need to understand the chemistry of life. So now we come into the idea about habitability. So we have a general idea about life, LEUCA, and now let's try to understand the idea of habitability. Now, Monday evening, not a time for a party, but let's think about it. So what are the different important elements for a party? The most important elements are the guests. So you need guests for a party. Those are the hearts of the party. You cannot have a party without the guests. The hosts are the second most important thing, because the hosts are those, the hosts make an environment so that the guests can have a good time. They can interact, they can bond, they can form meaningful relationships during that party. So the hosts are also really important. And the third very important point is the food. You cannot have a party without food. So you need food to sustain the party. As always, like in any party, we'll have people with serious dietary restrictions. And we'll understand that life too has serious dietary restrictions, and we'll learn about those really soon. So let's take that idea of a party and think about life. So what are the most important? What does life require? The most important thing are the elements. You need the elements to build up life. So you need elements like carbon, hydrogen, oxygen, sulfur. These are the CHNOPS elements. We call them CHNOPS or sponge. And these are really important as the building block. So you need to bring all these different elements together. And you have to bring in metals like iron, zinc, even arsenic for life. So you need iron for hemoglobin. You need zinc for the functioning of different kinds of metabolisms. So you need different kinds of elements. These are the building blocks of life. The second is the medium, liquid water. Why liquid? Because if you have a solid medium, it's really dense. So there is no mobility. If it is gas, it's really diffuse. So you do not get the concentrations. Anything in liquid form will give you the perfect medium for all these different guests, the elements to come together and interact and form the building blocks, form the biomolecules like protein, carbohydrates, and things like that. Water is the most important medium for life as we know it, because it's really available in our solar system. Like it's available because of its stability zones. It is stable on different kinds of planets. And we'll look into that in the habitability, in the habitable zones part. And we'll also look into why liquid water is really important. Why can't you have liquid ammonia? We'll talk about that. And the third thing is energy. So you need energy for life to eat. So life needs to sustain itself, which we call it metabolism. So life needs energy. And life will also have serious dietary restrictions, and we'll look into that. Let's first briefly look into this building blocks or the elements of life. Before going any further, are there any questions in the room or in the chat?
No questions yet.
Are
No.
there any? Okay. Cool. So let's look into the elements. So as I said, we need different kinds of elements. So this is a chart which you might have seen this, in which on the x-axis we are plotting the different atomic numbers. So you start with hydrogen and move out. So you see hydrogen is being formed by Big Bang nucleosynthesis, and then you form these different kinds of elements. The C is here, oxygen, nitrogen, all these kinds of different elements which are really required are being formed by stellar nucleosynthesis. Now, there are other different kinds of elements that are also required. As I said, we need the metals. They're also formed in end-stage stellar nucleosynthesis, but we are not going into that. I'm just trying to impress upon you that we can form these different elements through different processes in the solar system. And these basic elements, the CHNOPS elements, the sponge elements, they make up 97% of all the biomass that is available. So a lot of all these CHNOPS elements that might be formed by Big Bang nucleosynthesis and stellar nucleosynthesis, and in great amounts. You see on the y-axis, you're plotting the abundance. They're really abundant. You can form these different kinds of elements during the various different kinds of nucleosynthesis processes that occur in the solar system. Now, on Earth, we have seen that the life forms that we have are carbon-based. So why do we have a carbon-based life? Because of basically 4 reasons. Because of the tetravalency of carbon. So carbon can accept 4 electrons, donate 4 electrons. So that gives carbon the potential for forming 4 covalent bonds, right? 4 tetravalent, it's a tetravalency of carbon is one of the major things. On top of the tetravalency, we have catenation, in which carbon can form straight chain compounds, like, as you can see in the figure in here. It can form branch changed compounds. It can form rings, and it can also form compounds that have double bonds. You can also have triple bonded carbons, and so on and so forth. So there's a various different forms of bondings that carbon can support. This unique property is called catenation, and this makes it important that we have a different field of organic, we have a different field of chemistry, organic chemistry, that deals with carbon and its compounds, except a few, like carbonates and bicarbonates. They do not get into organic, but carbon can form compounds. That's what it does. If you're a Star Trek follower, like, you can have silica-based life too, but let me not get into that whole thing. So the carbon is a really versatile element, and it really forms different kinds of organic molecules. So that is why it's really important for life form as we know it. At least carbon is really important for that. It can form different kinds of biomolecules. So it can form lipids, nucleic acids, carbohydrates, and proteins. I will quickly go through this because this is a really basic idea, and I'm not an expert on these things. So I'll just quickly note that there are nucleic acids that similar like DNA and RNA that carry the genetic code. You have proteins that are polymers of amino acids that have different kinds of functions in our body. They can form the structural molecules like keratin, like our hair, keratin in our nails, so they give the structural stability to many of these molecules. They also serve as energy. They're really important in energy production in the ATP, so adenosine triphosphate, those kind of cycles. And they can also serve as enzymes or biocatalysts during different kinds of reactions that happen in life. Really important. Carbohydrates, sources of energy, of course, and storage of energy. And then you have lipids, which are really important molecules that have a long hydrophobic chain, in which you see this carbon chain, which is the hydrophobic. It's repelled by water. And then you have this COOH chain, which is kind of obscured in here. That is the hydrophilic part. And this becomes really important in forming the cellular membrane structures. Also, lipids are good for energy storage, the fat molecules. So 4 basic molecules of life, which are called biomolecules, giving a general idea about the different elements, the structural component. Now, organic carbon is really common in the universe. It might be strange to think about it, but you can form organic molecules, and you can actually detect organic molecules in different kinds of settings. In the circumstellar envelope, so this is a stage in which the solar system hasn't even formed. So even before the genesis of the solar system, you can have the circumstellar. So this is the star in the middle, and this envelope that is surrounding in here has shown that there are organic molecules surrounding this birth of the star. Moving forward to molecular clouds, which are really cold and really dense, you also form organic molecules of slightly higher molecular weight than these circumstellar envelopes. You can have carbonaceous meteorites. So there are different kinds of meteorites. You might have heard about carbonaceous chondrite meteorites. So this is the Murchison meteorite that fell in Australia in 1969. And when it fell, people reported that they could smell solvents because it was so hot when it fell, the organic compounds that were inside that started to burn. So this meteorite, along with several other, have so much organic compounds in them. Organic compounds are really common in the solar system. For comets, you might have known that comets have really high organic matter content. So this is the 67P comet that we have actual data from. So we were able to, humanity was able to actually get the samples off of this meteorite. And there has been so many other missions, like we have the Ryugu meteorite sampling mission that happened like last year. So we have so much evidence that we have organic matter everywhere in the solar system. Even Mars has organic matter, and we'll see about that. So since we think that organic matter is so common, what's the problem? The problem is we can have organic matter, but these are simple organic matter. These are not the polymers that we saw earlier. These are simpler molecules which need to form the polymers in specific circumstances, like in specific environmental conditions. So we'll look into these processes later, but for now, understand that organic matter is common on the surface, on different parts in the universe, but having complex organic matter in huge quantities is a problem. And that is the bottleneck in most of these cases. Now, let's move into the second most important thing that is needed for life, which is water. Water, as we call it, the elixir of life, is important because it's so abundant in our solar system. You have liquid water in a lot of places, maybe freely flowing, maybe absorbed in the minerals, but we have liquid water at so many different kinds of planetary bodies, planetary surfaces. Water is a polar molecule. That means it has, so we have an oxygen, we have hydrogen, and a hydrogen. So this molecule, oxygen, is sp3 hybridized, but I'm not going into the details of this. So because of the oxygen being sp3 hybridized, the shape is bent, and because of this bent shape, this oxygen is a more electronegative atom, and this pulls in the electrons in this direction, pulls in the electron in this direction, and generates a delta negative charge on this. This develops a delta positive charge, and this is the genesis of the polar nature. Now, when you have a polar compound, this dissolves polar solvent. A polar solvent will dissolve polar solutes. So that's an idea of the like dissolves like. So we call water the universal solvent. So water, being the polar molecule, can dissolve a lot of the different elements and the different amounts of salts that might be really important for the genesis of life. So ammonia, for example, or methane is not a polar molecule. So that is why it might be really abundant on the surface of Titan, for example, but since it is not polar, it might not be able to dissolve the different elements that are required for life. So the polar nature of water is really important. That also forms this hydrogen bonding. I do not know how much people appreciate hydrogen bonding in real world, but life depends on hydrogen bonding. The DNA structure is based on hydrogen bonding. So what is hydrogen bonding? Is the slight interaction between hydrogen and a really electronegative element like oxygen or chlorine or nitrogen or fluorine, for example. In this case, this interaction, this dotted interaction that you see in here, that is bounding this water molecule to, say, this water molecule, is this dotted structure is the hydrogen bonding. This dotted structure is the hydrogen bonding. This is the hydrogen bonding. Because of this hydrogen bonding, because of this slight interaction, which is midway between a really strong covalent bond and really not stronger London dispersive forces, for example, this intermediate bond strength is really important for the stabilization of life, for DNA stabilization, for example. So water is liquid for that reason. Let me digress just a little bit on this. So, you know, H2O is liquid at normal room temperature and pressure conditions, and H2S is a gas. H2S has more molecular weight. When you increase the molecular weight, the tendency is to become more dense. So it should go, so if this is liquid, this should at least be a liquid and probably go to a solid state. But hydrogen sulfide is not, it's a gas. So how can a lesser molecular weight compound be liquid and not gas? The reason is hydrogen bonding. The hydrogen bonding brings in these different hydrogen water molecules together and stabilizes water in the liquid form at normal temperature and pressure conditions. So hydrogen bond is really important. That hydrogen bonding is also stabilized. That also is the reason for ice being less dense than liquid water. I'm not going into the details of this because that will like really digress me from the topic, but all these different kinds of things really make water the elixir of life. Now, we'll see at what temperature and pressure conditions liquid water is stable on different planets. That will give rise to the idea of planetary habitability. Because if you are if the temperature is too high, you get into the vapor phase. So if you're really close to the sun, liquid water won't be stabilized. If you're far away from the sun, you get ice. You need stability of liquid water. And that can only happen in I'm new with this pen thing, so please excuse my stupid annotations. So in order to have this liquid stability, we need to really have a temperature condition, and we'll use this concept when we define habitability or habitable zones in our solar system. Now, let's understand what are the different sources of energy. Like the third part, we have elements, we have liquid water. Let's think about the sources of energy. Okay, so let's go back a little bit really quickly and understand what an atom is. An atom is protons, neutrons, and electrons. Protons and neutrons are in the nucleus. The electrons come in different orbits. And the most important part of any atom is the outermost shell, because that is the shell that allows the transfer of electrons. The outermost shell being the most active part, and rest everything I'm giving the name of kernel. So an atom is basically the valence shell and the kernel. Okay. Now, when you have an electron transfer from the outermost electron, say you lose an electron from the outermost shell, that loss of electron generates a positively charged cation and an electron. That positively charged cation has increased its oxidation number. This means when you have a carbon which is neutral, and when an electron is lost, the oxidation state, which was 0 in this case, went to +1, right? Really simple. So increase in oxidation state due to loss of electron is termed as oxidation. The other way, the opposite of it is reduction. Gain of electrons. When an atom gains an electron, it forms a negatively charged anion, and this process is called reduction. Reduction in what? The oxidation number. As you see in here, the oxidation number of carbon went from 0 to -1. So both these processes together is called redox. So this is a very simple reaction. You might have recognized this as simple photosynthesis. So redox is a process which is basically reduction of electron and oxidation of electron. In this case, carbon is reduced because the oxidation state of carbon went from +4 to 0, and oxygen of the water molecule went from -2 to 0. So the process of reduction and oxidation happened together in this molecule, and this is called redox. I wanted to get this out because when I say redox, there are some people who might not be really familiar with this terminology, but it is just a really simple term to bring in transfer of electrons. Loss and gain together is called redox, simplistically speaking. Now, you can have not just carbon, but you can have things like iron 2+. So when an iron atom loses an electron, it forms iron 2. So Fe, when lost 2 electrons, form Fe2+, and then this Fe2+ underwent one more electron loss and formed the Fe3+. So Fe2 to Fe3+ is oxidation of Fe2+. Reduction of Fe3+ brings into Fe2+. All these different kinds of things can be happening in different kinds of elements. So this is redox. Why I am talking about redox, we'll soon understand why. Transfer of electrons is really essential for life. I'm just keeping at it right now, and then we'll come to this later. Now, let's understand one more simple concept of energetics, in which we try and understand how, when a reaction happens, some reactions are favorable while some reactions are not. And how we know some reactions are favorable? Because the favorable reactions will only happen when there is a decrease in energy. Why are we sitting in this room? Because we want to gain stability. How do we gain stability? Everything in this universe wants stability. Everyone, you, me, everyone wants stability. Even the electrons, even the atoms, they want stability. How do things get stability? They lose their energy, simplistically speaking. So if in the x-axis we have the reaction progress, and on the y-axis we have free energy or energy, anything that will decrease its energy will inherently become more stable. Think about kids, they are so energetic. But we, on the other hand, are less energetic. We have less energy, and we have exchanged that energy for more stability. I mean, at least we can assume that we have done that. Okay, so we went from, so as reaction progresses, you move from reactant to a product. In this case, the energy of the reactant was more than the energy of the product. So the free energy exchange, like what happened was energy was released at the end of the process. When energy is released, that process is feasible, and we call it the delta G of the reaction, or delta G is nothing but it's the free energy. So G is the free energy, and delta G is the change in that free energy. The change in that free energy is negative because energy of the product minus the energy of the reactant was a negative reaction. Now, this is a feasible reaction because the energy was reduced. This is a chemical disequilibrium because the energy of the reactant was not equal to the energy of the product. There is also chemical equilibrium in which the energy of the reactant and the product were exactly the same. So this reaction, this thing is called equilibrium. There is no energy, nothing is favored over the other. The reactant is not favored over the product. Now, the other is the product having higher energy than the reactant. In this case, this is still a chemical disequilibrium because the energies are different, but this reaction will not be feasible because you're increasing the energy. No one wants to increase the energy because when you increase the energy, you become unstable. No one wants that. Now, to reiterate, less energy means more stable, and redox means exchange of electrons, simplistically speaking. Now, there are different kinds of energies available in the solar system. There's heat energy, nuclear energy, sound energy, whatnot, different kinds of chemical energies, hydration energies, dissolution, redox. So you might be teaching your students in your classes all these different kinds of chemical energies. Of course, there's light energy, things like that. But remember the dietary restrictions that we talked about? Not many people will eat meat. Not many people will eat milk products. So they have dietary restrictions. Life also has dietary restrictions. It will not eat all these different kinds of things, but it will only eat redox-related energies and light-related energies, because both these involve transfer of electrons. Even light energy, when you remember photosynthesis, what actually happens is light interacts, and that influences transfer of electrons, that facilitates transfer of electrons. So when you have transfer of electrons, only that, so that process is called photosynthesis. What photo means light, and synthesis, what are you synthesizing? Energy. So photosynthesis involves transfer of electrons facilitated by light, by UV or light of a particular wavelength. So that life can utilize that energy. You can also utilize energies related to redox processes, the transfer of electrons. So if you have a transfer of electron and an energy is released, that energy can be utilized by life, by bacteria, by archaea, by eukarya, stuff like that. Now, this becomes important because we can have different kinds of energies everywhere in our solar system. But since we have a limited supply of light and a limited supply of redox synthesis, redox-related energies, we need to be really careful about when we are trying to learn about life and what kinds of energies it can actually utilize. All right, so yes, so life has serious dietary restrictions. You'll only use two types of energies: chemosynthesis and photosynthesis. Really important. This will become really important because Earth has light, but there are certain worlds that might not have light. So there are ocean worlds way back, way into so Earth is about 1 astronomical unit from the sun. It has light. So Jupiter is 5 astronomical units away from the sun. The moons of Jupiter, like Europa, has huge ocean worlds, and we look into that. So it has ocean worlds, so it has a lot of water, but it has no light. So if we are trying to find out life on Europa, we cannot be looking into photosynthesis because there is no light. We have to be looking into chemosynthesis, the redox reactions that we talked about, the transfer of electrons and the energy that it produces. Okay, having said that, let's understand, because most of our understanding of life comes from the emergence of life on early Earth. I will not move into a whole lot of detail because this course is about life on Mars, but just look into what do we know slightly about life, the emergence of life on early Earth. So this is a diagram that I showed you earlier. So the oldest microfossils were here, and they look something like this. So we have stromatolites growing in Western Australia that showed that there might have been organisms that was growing at that time in those pond, kind of like shallow pond kind of deposits, and that raised microorganisms and microbial mats, and these give rise to these microbial mats imprinted on these rocks. We call them stromatolites. There are other different kinds of microfossils, and we'll not talk about those. You might have heard about the hematite nanotubes that were formed about 3.7 billion years ago. So there are different kinds of biomarkers, if we say, that existed on early Earth, and that's how we know that life emerged on early Earth. We have also fossil records that go to Ediacaran fossils and stuff like that, 3 billion years or so. Different ideas of emergence of life on Earth. But let's do some experiments and try and understand whether the situation of life in these kind of early environment was there. Can you actually show by experimentation that Earth had the right conditions for developing life on early Earth? And since this is like a half an hour, do we want to take a 5-minute break, perhaps? Or
Yeah, I think we need a 5-minute break.
cool. Yeah, we'll reconvene at 6:40.
Okay, thank you.
Yeah, most of it's still. Yeah, my wife and I just moved into the house in the building, so I know it's too short. Been GCing that project since April of last year. We find it, people on the box down, just the way, unpacking our life, just in storage, on cleaning items to that, but yeah. My wife had to force me to hire a lot of folks that probably I could have done the work, just to multiply my existence and be in more places. Too. So, it's been cool. Are a lot of bombs down or not? They're in good shape. They're in good shape. They're just trying to do the listening about those steps. Yeah.
I don't know if you're interested. I was just showing these books.
Oh, yeah, very much. I saw it. Apologize. I showed that.
No, that's fine.
Yeah, because it's exciting.
Cool. It's 6:40, and I think I'll resume.
Yes, please.
Okay, so we had geological evidence of life, of past life through fossils and other different kinds of mineral records. But there was this really interesting experiments that Miller did at Chicago with a really famous scientist called Urey. So Urey was one of the giants in geochemistry, and it's still is regarded one of the greatest geochemists of all time. So Miller was a student. So they did this primordial soup experiment, as I call it, in which they were trying to understand whether Earth had enough material to form, or did Earth have a good environment to form organic molecules, specifically amino acids for proteins, on early Earth. So this is an experiment that they did, in which they started with a source of water in here. So they boiled liquid water, and this water is being fed in here, and you source different kinds of gases. So what Miller thought that these are the different gases that you might have on early Earth: methane, ammonia, hydrogen, and water that you're feeding in from here. So water vapor. So when you have these different kinds of gases in the atmosphere, and if you had UV light or electrostatic discharge on early Earth's atmosphere, what kind of reactions are actually taking place in that environment? So they did this experiment. They had an electric discharge passing through these different kinds of gases, and then they condensated these different molecules that formed, and then analyzed this. What they found was a lot of amino acids, along with other different kinds of organic molecules, formed at the end of these experiments. This was a revolutionary experiment that was done at that time. It was probably 1950s, 1960s, in which people actually were able to experimentally demonstrate that the early Earth atmosphere had enough starting materials to form organic matter on the surface of Earth at an early Earth time period. Now, remember that the Murchison meteorite that I told you before, this is a carbonaceous chondrite CM type meteorite. So meteorites are generally differentiated into chondrites and achondrites. This is a chondrite meteorites that have chondrules in them. And then in chondrites, you have carbonaceous chondrites. So Murchison is a type of carbonaceous chondrite, and we call them CM chondrites. So these are just jargons, but understand that this is a carbonaceous chondrite, and this was in 1969, probably we got hold of this meteorite, and then a lot of analysis was done on what kinds of organic molecules that the Murchison meteorite had. And it also had a lot of amino acids like glycine and alanine and other different kinds of organic meteorites. So this was done in 1950s, and this was done in, say, 1970s. And then people found out that a lot of these molecules that were found in both were common. Like you found glycine in both this experiment and in the meteorite. And so for different kinds of organic molecules. So these are amino acids. These are different kinds of higher variations of amino acids that are really important. Why do we focus on the amino acids that much? Because these are the building blocks of proteins. Now, the different dots in here shows that the abundance. So the glycine is the simplest amino acid, and this was like really abundant. And say hypochloric acid, whatever that is, I do not know, was really less abundant. So through these two, we were able to understand that not only organic matter is common in different parts of our solar system, these could be easily be forming on the surface of early Earth way back when. There are some caveats to these experiments that were done. The choice of the starting gases have been questioned recently, and we have doubts that you have do you have methane and ammonia? Do you really have methane and ammonia in the atmosphere of early Earth? So although like this is disputed right now, but this gives us a sense that if you have electrical discharge and you have organic molecules, it is really easy to form organic molecules in different kinds of settings. And that is why you have organic molecules in the circumstellar medium, in molecular clouds, in organic, like in carbonaceous meteorites. And there might be some in comets, and it could be possible to form organic molecules on surface of early Earth, although it is disputable based on these experiments. But it's relatively common. As I said before, the difficulty is not in making these organic molecules. It's really easy to form these molecules. But the hard part is to form certain kinds of molecules, which are basically the polymers of these smaller ones. So the difficulty is making these, the monomers come in. So 2 or 3 different kinds of amino acids come in together, and then they form the polymers of these amino acids, and they form proteins. The different kinds of sugars come together, they form carbohydrates. The different kinds of lipids come together, and they form the polymers. So what the difficulty in making these polymers is, when these different kinds of monomers come in, you need to like remove water to make these polymers. So if you have a lot of water, the polymerization reactions are not being favored. So that is one of the reasons that we have difficulty forming these biomolecules. So you need a setting in which you do not have a lot of water, but you have just enough water to facilitate these polymerization reactions. So it's not the amount. So you can have a lot of amount of water, but that might not facilitate life. Because if you have a lot of water, first, the solutions are dilute, and we need concentrated solutions. And another thing is, you do not form polymerization reactions when you have a lot of water. So you need a dehydrating situation to form these, to favor the formation of polymers. But if you have too little, then the reactions comes to stop. This is how I understand. It's a very special circumstances in which life molecules must have formed. And we still do not have a clear-cut idea what all these different circumstances were. So there has to be a million things going correct to form like the biomolecules or the origin of life. And the origin of life might be taking place not just in one place. It might be happening in a shallow pond. It might be happening in a hydrothermal vent system that we have on Earth near the mid-oceanic ridges. There can be different kinds of settings, but all these different kinds of settings needs to form these different kinds of biomolecules in enough quantities so that life can trigger, like life can be triggered. That is the difficult part. It's really easy to make simple molecules in dilute concentrations, but making bigger molecules in concentrated solutions is the challenge of life. Now, these are the different kinds of biomarkers, as I briefly mentioned before. So this is the stromatolite that I showed in Western Australia before. And these tubes that you see are nanohematite tubes, and hematite is Fe2O3. that have been suggested to be the oldest microfossils available on the surface of Earth. And so these are about 3.7 billion years old. A little debatable, but yeah, there are different kinds of biomarkers that exist. So the biomarkers doesn't always have to be fossil records like the dinosaurs. They can be really subtle, like the stromatolites or these hematite nanotubes. You can also have isotopic evidences. Now, we know that different elements have different isotopes. So sulfur has different isotopes. And what is an isotope? An isotope is two atoms that have the same number of protons in them, but the different number of neutrons. So, for example, if you have carbon, I'm taking carbon because this is most relevant for organic molecules. So say you have C6, you can have a 12. So in this atom, you have 6 protons and 6 neutrons. You can have carbon 13. In this, you have the proton number remains the same, 6, but the neutron number is 7. So these are isotopes of each other. So these two are isotopes of each other. So this is the heavier isotope, this is lighter isotopes. Now, life favors one isotope over the other. So in this diagram, you see that there is a way of representing or calculating the different kinds of isotopes. I'm not going into that because isotope geochemistry is a whole field in itself. So in this thing, what I'm just trying to impress upon you is life is selective about which carbon isotope it's going to select. Now, if we analyze the different kinds of isotopes, we might be able to understand whether it was life that did that selection or whether it was some inorganic process that did it. So based on isotopic studies, you can also find out, like, the biomarkers doesn't only have, they don't have to be something like a fossil that you can see. They can also be really subtle, like the isotopes that we can analyze in the labs. So based on the different isotopes that you have, you can safely say whether these are indicators of past life or not. All right, now this brings me to the different kinds of habitable zones in our solar system. Why this is important? Because we know that the 3 basic elements are, the 3 basic things that you need for life are the elements, the energy, and the stability of liquid water. The stability of liquid water becomes a really important aspect because you have different kinds of elements. You have carbon, you have oxygen, hydrogen, sulfur, all these different kinds of elements everywhere in the solar system. And that is why you have organic molecules everywhere in the solar system. So like even before the solar system existed, elements existed. So having elements is not the problem. Having energy is not the problem, because when you have these different elements, there will be reactions going on between these different kinds of elements. Liquid water kind of is the bottleneck that determines whether you will have these different reactions in that aqueous medium or not. And what determines the stability of liquid water? The pressure and the temperature. More importantly for Earth, more important for our solar system is the pressure. So is the temperature, because the sun is like that big force that kind of rules most of the things that happens in our solar system. So we needed to understand what are the different zones in our solar system that can stabilize liquid water on the surface of different planets or on the subsurface of different planets. And that's why we come to this idea about habitable zones in our solar system. Now, the basic idea is really simple. So you need to be in just that right temperature range in which liquid water can be stable. Because if you're too cold, too far away, you form ice. If you're too close, you form like vapor. So you don't form liquid ice, liquid water. So you need to be in that Goldilocks zone for liquid water to be stable. So we have these habitable zones around the solar system. So for example, So Earth, so our sun being a G class of star, so there are different kinds of stars. So there are O, D, F, G, K, and these are different kinds of stars that are there in the solar system. So O's type of stars are the biggest ones and the most, like the hottest ones. And when you move from the hottest ones to the coldest ones, this is how it forms. So M is the smallest and the least hot star type available in our galaxy. Now, when you have a star like G type of star, so let's focus on just the G type of star because that's what our sun is. So when you're too close, so this is the stellar distance. That means the amount of the distance that you are from your parent star. So, so this is Mercury, this is Venus, this is Earth, and Earth, as you see, is about 1 astronomical unit far away from the sun. You see that when you're too close, you're in this hot zone. When you're too far off, say in here, you will have Jupiter. Sorry, Jupiter is somewhere in here, about 5 astronomical units. So it's way in here. So you're really in the cold zone. But if you have a hotter star, so when you have a hotter star, this hot zone kind of increases in its region. And when you're closer to the star, then the distance in which liquid water stabilizes kind of like shrinks in this manner. So in a bigger star, there's a lot of a hot zone in here. In a colder star, the hot zone is not. So for a colder star, if you need to find a planet which has the right amount of like temperature coming in, you have to be really close to that low temperature star. But if you are in an O type of star, say, so you'll really have to go about farther away from the sun to be in that habitable zone. Complex kind of, calculations go into this. So this paper was written by a scientist in UPenn, and this paper has been cited over like 2,000 times or stuff like that. Like the habitable zones around stars is a highly sought out paper in our community, and a lot of research is going on still. I'm not going into the mathematics of it. There's a lot of things that goes in, but simply understanding the idea that as you move towards the sun, it becomes more hotter, and you move too farther away, it becomes colder. So somewhere in between, there is a habitable zone that stabilizes liquid water. All right. Now, there is this paradox of liquid water availability and organic availability. Now, as we see that liquid water becomes ice when it goes too far away. So you have this H2O ice line. So if you move far away, say 4 astronomical units, you hit the H2O ice line. That means after this, you will only form H2O ice in any of the planetary bodies. So if you have water on a planetary body, which is 4 astronomical units or farther away, you form ice. So in order for ice to form, you need to be before this. Now, organic matter, because it is so much volatile, more volatile than Earth, more volatile than liquid water, it will form in a region that is farther away from the liquid water zone. That means these PAH are polycyclic aromatic hydrocarbons. So these are really complicated hydrocarbons. And this polycyclic aromatic hydrocarbons only exist about 2 astronomical units. Anywhere after this, you form ice. Anywhere after this, you form PAH. Okay. Now, but we saw that the habitable zone in this case was somewhere in this region. Now you see the habitable zone for our star is between this, say, 0.75 to 1.5 astronomical units. So liquid water can only be stable between, say, 0.7 to 1.5 astronomical units. So this is where liquid water is stable. But where is polyaromatic hydrocarbons stable? After 2 astronomical units. So liquid water and organics, they are not stable in the habitable zone. Now, this is the big paradox. So you need organics, you need liquid water, but they both are not stable at the same habitable zone in the solar system. Now that's the big problem. Now this H2O ice, now in this region, say, you can have organic matter present, you can have liquid water present, but this gives a very small area. I mean, these different kinds of estimates vary a lot. So in this case, this says at 4 astronomical units, you will form water ice. In here, it says at 1.5, you will form liquid ice. Water ice, right? So in this calculation, it says it's after 1.45 astronomical units, you will form ice. And in this case, it says you will still have liquid water present in this small region. So there could be regions in our solar system in which liquid water and organics can be stable together. But these calculations are so big picture calculation. There is so much uncertainty that we cannot be really sure about the coexistence of liquid water and organics in a big picture idea. So the understanding this is a little bit tricky and probably counterintuitive, but I just want to reiterate that at certain point where liquid water is stable, aromatics might not be stable. And when you have the aromatics stabilizing, liquid water might be going into the ice form. So having liquid water and the ice, having liquid water and the organics at the same point in the solar system is kind of like the difficulty. And this is the paradox that I'm talking about. Okay, now let's talk about the different planetary bodies with the maximum potential of life. Now, when we know where the different kinds of the habitable zones in our solar system, let's talk about the planetary bodies with the maximum potential of life. Earth, of course, but we are not talking about Earth because that's a very different area. Let's talk about the different elements of life that we have, and then try to figure out what might be the different planetary bodies that might have the liquid water. So we know that we need the elements, we need the medium, liquid water, and we need energy. So basically, we need planetary bodies with liquid water on their surface or in their subsurface, and we need to be thinking about the redox processes that happen in these bodies, because light is really not that much available after Earth. And also, the sun is a growing star. So a few billion years ago, the sun, our sun, was not as bright as it is right now. We call it the faint young sun problem. So when life originated on Earth, or maybe on Mars, or any other planet in our solar system, light was not that much available because sun was not that much bright. It was a faint young sun. So we need to really be thinking about the redox processes that are occurring in these aqueous systems in these different planetary bodies. What are those? Except Earth, don't think about Earth. Mars could be one. So Mars in past had liquid water. We have geomorphological evidence and we have geochemical evidence of liquid water on the surface of Mars. And the second lecture will be investigating more on the nature of liquid water that existed on Mars in the past. And there is still some liquid water that exists on the surface now, in the subsurface, on the poles, things like that. But there was some light, perhaps, and these are giving rise to concentrated solutions of like in which the elements, all these different kinds of elements, iron, manganese, the sponge are getting concentrated because the amount of water is slight. It's not that much water like that we have on Earth. Now, we can also have different kinds of ocean worlds, and we'll look into those. So you might have heard that there are moons of Jupiter and Saturn farther away in our solar system that are termed as ocean worlds. They have huge amounts of liquid water in their subsurface. Their surface is made up of about, and the ideas like vary about how much thick the ice is, but anywhere between 10 to 100 kilometers of ice, and then we have liquid water in the subsurface. So we have ocean worlds like Europa and Enceladus. Now, since they are really farther away from the sun, they were not supposed to be in the habitable zones, but they are now. We'll talk about in the few slides to come why there is a new Goldilocks zone in those kinds of, like we had a Goldilocks zone in the solar system, but we have a new Goldilocks zone around Jupiter and Saturn and these massive gas giants. But we have a lot of water in these ocean worlds. So these are ocean worlds. They have a lot of liquid water, but that brings in a different problem. The solutions are really dilute. So we'll think about that a little bit, but not a lot, because Europa and Enceladus and each of them merit like a course, a full-fledged semester course on their own. Like we have books like those written on Europa and Enceladus. Mars is one of our focus because we'll see the red color in itself is a really good indication that there was something special going on. Red on Earth generally means hematite, iron oxides. And hematite means there was iron oxidation in presence of liquid water. So that is one of the primary reasons that, and that is one of the primary driving factors of NASA investigations for Mars. The red color and the reason for the red color of Mars. Why did it form the red color that it has today? What does that mean? Is there only hematite, or are there other minerals that form? My research, my PhD research was focused on finding out this age-old question, whether it was oxygen. So whether it was oxygen that formed these iron oxides on Mars or not. Because on Earth, rusting that produces this iron oxide is closely tied to oxygen in the terrestrial atmosphere. In my research and in an article that I just published, in an article in a journal, I refuted the idea of oxygen in the early Martian atmosphere, and I showed that there was no oxygen or extremely little amount of oxygen in the Martian atmosphere in the past, and it was something else. And if time permits, we'll talk about that something else sometime later. But Mars is one thing. There is a new Goldilocks zone that exists in our solar system that surrounds the gas giants like Jupiter and Saturn. So imagine that you have Jupiter somewhere here. So you have Jupiter in here. And these are the different planets, like the planets that are orbiting the sun. So Jupiter is the analogous for sun in here, and these different moons of Jupiter. So this is the moon Io, this is Europa, this is Ganymede, I'm sure I messed up this spelling there, and Callisto. So these are the different, there are several moons, 40 some, but these are the most famous ones. And these are the Galilean moons of Jupiter, because the great Galileo Galilei, he was able to see this through his telescopes way back when. So he identified these, but he did not know that how interesting these different moons of Jupiter were. So Io is really volcanically active. So we have seen active volcanoes on the surface of Io. And these yellowish, greenish color thing is basically the sulfur dioxide and the sulfur gases that are coming out. Io is the most volcanically active planetary body in our solar system, more active than planet Earth. Volcanic eruptions are like really common on the surface of Io. So really high volcanic activity. You move farther out, so you might think that this is like the really hot zone. These two are kind of in the Goldilocks zone, in which you have ice on the surface, but you have liquid water, oceans deep within, just below the surface of Europa and Ganymede. We have confirmed evidence of liquid water on the subsurface of Europa and Ganymede. In the next decade, NASA is sending Europa Clipper mission as an orbiter to Clipper and as an orbiter to Europa to find out more about the life and habitability on Europa. And ESA's, the European Space Agency's JUICE mission, is going to Ganymede for understanding the same for a different Goldilocks planet, the Ganymede. It will also have a flyby of Europa, but JUICE mission is basically focused on Ganymede. Now, Callisto is like really cold, and it has like really thick oceans, really thick crust, and really small amounts of liquid water as compared to Europa and Ganymede. So this is the new Goldilocks zone that has been that has been discovered around massive planets like Jupiter. And this is because of the tidal force, because Jupiter is such a massive planet. The tidal forcing of Jupiter is the energy that is supporting the high volcanic activity of Io and the stability of liquid water on Europa and Ganymede. For the sun, it was the solar insolation, the heat from the nuclear fusion reactions happening on the surface of sun that is giving that energy. In the case of Jupiter, it's not nuclear fusion, it's the gravitational locking, the tidal locking. The gravitational forces are actually producing this heating up of Io and stabilizing the liquid water on Europa and Ganymede. Now these are primarily my area of focus. In my research, I focus on Mars, Europa, and Enceladus. So Enceladus is also, so this is Enceladus, really small moon, but really interesting moon of Saturn. And in the past, we had seen plumes jetting out from the southern pole of Enceladus. So you can check it out. Like, we have so much evidence of actual cryovolcanism coming out of Europa, and Enceladus. And it's really interesting to know that we have been able to sample the plumes that were jetting out of Enceladus. We were able to capture these cryovolcanic jets that were coming out, and we have found that it has a lot of silica, it has a lot of sodium bicarbonate, really interesting things coming from the oceans beneath. Now, why silica is important? Because we think that there might be something similar to a hydrothermal vent system on Enceladus. So this is Enceladus with its plume coming out. This is Saturn. So when we saw SiO2 in here, we think that the silicon dioxide is coming from the interaction of this rocky core, as it's mentioned here. So the rocky core is interacting with these ocean and generating these silica and other different kinds of interesting carbon-containing things in these oceans, and that's what we are able to capture. Now, understanding the ocean chemistry is one of the leading science questions right now, both for Europa and for Enceladus, although we have not found definitive evidence of plumes coming out from Europa, but we do think that similar kinds of processes, these ocean surface interaction might be going on Europa and Enceladus both. So understanding these compositions are a different frontier of astrobiology right now. Now, coming back to Mars, Europa and Enceladus are their own courses, but is Mars habitable? Do we have any evidence of liquid, of any amount of evidence of habitable or organic matter that has come from Mars? The answer is yes. There was a meteorite called the Allen Hills meteorite. So Allen Hills is a place in Antarctica, and people usually go there to get meteorites, to collect meteorites. So there was a 1984 mission that went to Allen Hills in Antarctica, and they found this meteorite, which is named ALH 84001. And we found these kinds of fossilized structures in the meteorite itself. Although the meteorite was an igneous meteorite, but one could argue, and people did argue in 1996, Mackay, there was this person, the scientist from NASA, he argued that these are the relics of previous Martian fossilized material that were entrapped in this meteorite. So that's what that person argued. So although this was primarily silica, there were carbonate deposits, carbonate minerals in the same meteorites, and had isotopic ratios that could be argued to be relevant for relict fossils on Mars. So carbonate evidence, things similar to microfossils, one might argue, were there. We also had magnetite. So magnetite is the mixed oxide form Fe3O4 of iron. So this is FeO and Fe2O3, magnetite. And we have seen crystals of magnetite like this in different thin sections of this same meteorite. And we know, so this is an image of an organism called magnetotactic bacteria. I'm sorry, magnetotactic bacteria, which have methane crystals like these inside its body in its chromosome. So when you actually found these things and these microfossils and these carbonates, there was a general idea that it could happen that the ALH 84001 was a proof of life on a different planet. There were two papers that came out back to back, and they both were from NASA scientists, Johnson Space Center, in which Mackay led the idea that there were actual definite proof of life on Mars. And there was another paper which argued against it. So the current understanding is probably not favoring McKay, and we generally think that these are not definitive proofs of Martian life, and we'll discuss about why it was not in our third lecture when we discuss about Martian meteorites in short. But this Martian meteorite, so let me tell you that there was like the Viking experiments that were done in 1970s. We'll also discuss about those. So the Viking experiments were done right after the Apollo missions. So we went to Mars. NASA went to Mars with Viking missions, did some biology experiments in an attempt to find out whether it could find definitive evidence of life on the surface of Mars. It did not. Then there was kind of the interest of the space of the astrobiology community kind of like thought that it did not interest Mars. Mars was not an interesting world for astrobiologists and NASA scientists at that time. So there was less and less money being pushed for Mars. What this meteorite did was put Mars into focus once again. So after 1984, there were like more, and after this paper in 1996, there were more and more missions that started to come out. Soon after, like there were several missions on Mars that has come out, and as of now, we have definite evidence of organic molecules on the surface of Mars. So this is an example in which chlorobenzene, it's one of the organic molecules that is something like this, that have been definitely found out in drill samples at the Gale crater site by the sample analysis at Mars instrument on board the Curiosity rover. Not only this, there have been like a slew of organic compounds that have been found on the surface of Mars. What does that mean? Maybe that means there was conditions for organic matter production on the surface. Maybe it was derived from the comets and the meteorites, like the carbonaceous chondrites might have had those meteorites and it just deposited those things on the surface of Mars. It could be anything. We will discuss about these results in our third lecture, but I just wanted to let you know that we have definitive evidence of organic matter and also methane in its atmosphere, in the Martian atmosphere on the surface. But not all hope is lost. We have organics, but we do not know if there is life on the surface of Mars because it could be in the subsurface. We do not know. All our understanding of all these different kinds of rovers comes from the surface. We do not know what is going on that's a centimeter below the surface of Mars. So the sample returns from the Mars are really important in this regard, because then we'll actually be able to sample directly what is happening in the subsurface from Mars. Now, a whole lot of things have happened since 1996 till now. There were several orbiter missions in the past. There were different lander missions. Currently, we have the Curiosity rover working at Gale crater. We recently landed the Perseverance rover last year at Jezero crater. We have cool results coming from that. And we'll be discussing all these different results that we are getting from these different rovers and what are their implications for finding life in the next 2 lectures to come. And the basic idea that we'll be thinking about is we'll be following the water, because as we see, like water is the most difficult thing to pinpoint or like stabilize on any planet. So that's what NASA did, and that's what we will do in the next 2 lectures to come. So I would open the floor for any questions. Thank you for listening. See, there are many questions. Okay, I'll just start with the chat questions. How do the Aegis Sparrow has asked, how do the habitable zone determinations take a celestial objects atmospheric composition and greenhouse effects into account? Really good question, because when we have these different kinds of models in these models in these containing the habitable zones, we do take into account what kinds of effects these greenhouse gases, and specifically carbon dioxide, has in increasing the temperature. So if you have CO2, your habitable zone will shift. Like if you have CO2 on Earth, it will raise the temperature. So things that are not that warm will become warmer. So things that might have been in the colder regions might go into the habitable zones. So I have not gotten into the intricate details of that, but I'll be sharing research papers that actually go into the further details of that.
I have a kind of follow-up then.
Yeah.
So then how come when you were talking about like the young sun following and not being as hot, and how come or has anybody then thought about like Venus? Wouldn't Venus then be in the habitable zone if the sun was not as strong? Like wouldn't that have shifted it over a little bit more for like a place to look? Because then that kind of would make sense to me that you'd want to look a little closer to the sun. And then Venus, I think in that one graphic was like right on the border. So then wouldn't that put that like really more in the habitable zone before it like got too hot?
Yes, you're right. I'm like just reiterating the question for the audience in here. So since there was a faint young sun problem, so the habitable zone was probably closer to the sun for our solar system in the past, say 2 or 3 billion years ago. That would make Venus more habitable. It could well be like Venus could have been in the habitable zone, but currently Venus seems to be like a really hot, like more hotter than Mercury because of its runaway greenhouse effect. But that is why it's so important to understand what's going on Venus. So currently, we know little about Venus than we know about some of these comets and some of these asteroids that we have samples. The good news is the next like decade or 2 decades, there will be 2 Venus missions, to NASA missions to Venus, the Da Vinci mission and the Venera, the Da Vinci and I'm just forgetting the name. So there are 2 NASA missions to Venus. The Indian Space Agency, they're coming up with Shukriyan, that is happening sometime. The ESA, the European Space Agency, is coming up with Envision mission to Venus. And the Roscosmos is again attempting to go to Venus once again with the Venera D mission. So there is an increased focus on Venus that is coming up in the next decade to come.
Those would be like rovers, or is it
mostly orbiters? But in the past, so the European space, the Russian space agencies, Roscosmos, USSR failed a lot to land on Mars, but they are the only nation who were successfully landing missions on the surface of Venus. So Venera missions that they had were actually able to land. So I do not have too much information about what Roscosmos, the Russian space agency, has committed to right now, but we can expect them to do at least an orbiter. So Teresa Smith has asked, so in order to be habitable, you need liquid water and the right amount of organic matter. What are the chances? The chances are really less. I cannot give you the actual probability, like the mathematical probability of those things, because I'm not a mathematician first, and I'm not so much into like finding out these habitable zones. I'm basically a chemist, so I do not look into these kind of like chances, but I can imagine the chances will be really less. But there is so little that we know about these kinds of special circumstances, because as we saw about these extremophiles that were able to like grow in situations that we do not even expect things to grow and thrive. So even if you don't have organic matter, a lot of it, there might be certain places that might just be suitable for some form of life to grow. And like life is really robust, and it has been really interesting. So we are discovering new forms of life every year in the oceans, in different kinds of like places like the hot springs, in ice cores and things like that. Probability is less, but I think not all hope is lost. At what point in time would the sun have been classified as something other than a G-type star? So there is this whole main sequence star evolution path in which there is a birth of a sun, and then it goes through this main sequence type star evolution, and it moves on from becoming a smaller sun to becoming the sun that we have now, increasing its temperature, increasing its size, and then increasing its size to becoming an M dwarf and things like that. So at what point, I do not know the exact timing in which the sun has grown, but I'm sure that the main sequence of stars have a typical way of growing, when it follows a typical lifestyle. I'm not sure about what exactly that is, but I can look into that and come back with an answer the next time we meet. Could life form on a moon? I think yes, there is no reason not to believe. And on a moon, I mean, if we are talking about our moon, Earth's moon, the chances are less because there is so little water. But on these other moons that are the ocean worlds, there could be a lot of potential for life forming on them. Are the rovers still sending data back to Earth? For how long? So we have currently Mars Curiosity rover that is sending back data. We have Mars Perseverance rover that is sending data as of now. So interestingly, the Mars, for how long? We hope that it goes for at least 10 more years, because the Mars Exploration rover, when it first went there, had only promised 100 days of working. But the Opportunity rover went on for 14 years of service. It actually completed 45 kilometers of roving on the surface. So there was a long lifespan that it had. We hope the same for Curiosity. Curiosity started its journey in 2013. It's still going on 10 years. 10 years now in 2023. For Perseverance, we still think that at least 10 years. That fingers crossed for that.
I think that's the end of the questions. And we all would love to thank you for all this incredible information and the slides that you've shown us. And I guess everybody's looking forward to the next chapter next week. So
Cool.
thank you very, very much.
Thank you, Karen.
Okay.